Okay, let's take a look at question number 1 in topic set 5 about gases. This question tells us that we have a compound that has a density of 1.2 grams per milliliter, and we want to use this as the liquid in a barometer. And the question is, what would be the height of that liquid if the atmospheric pressure is 749 torr? Okay. And then the second question is, when would it be appropriate to use this particular liquid as opposed to mercury, which is our standard liquid that we use for barometers? The way we design a barometer is we take a tall tube, fill it up with a liquid, for example mercury, and then we invert that into a container that looks like this. And typically what you expect, of course, is all the liquid will drain out, but what happens is some amount of the liquid is staying inside the tube. And the reason that happens is because on the outside there is pressure exerted by the atmospheric gases, which then pushes this liquid back up and keeping it staying inside the tubing. And so the height of the liquid, H, corresponds to the pressure that's being exerted on the outside. So we can figure out the relationship between pressure and height by remembering that pressure is force per unit area, and force itself, which is gravitational force, is just mass time acceleration due to gravity. So if we multiply by H on the numerator and denominator, what we get is the bottom, surface area times height, and that's volume. And then we see that m over v, mass over volume, is just density. So basically the pressure is then proportional to the density of the liquid times the gravitational acceleration times the height of the liquid. And so this equation is what allows us to relate pressure of the atmosphere to the height of the liquid that we use. If you think about it conceptually, if the liquid is very dense, right, then it would take a lot more pressure to push it higher. Whereas if the liquid is not so dense, then it should take less pressure to push it up a certain height. And so the density also affects the height of the liquid. So height can be used to measure pressure. Now let's take a look at this question. Pressure is 749 torr. Of course, that's the same as 749 millimeters of mercury. So the pressure measured by mercury is the same as the pressure measured by these new liquid, the iododecane, right? They're both corresponding to that same pressure. Now, when you measure it with mercury, that corresponds to this height in mercury. So the question is, what is the corresponding height in iododecane? Well, let's rearrange this equation. The pressure is given by density of the liquid, which in this case is mercury, times gravitational acceleration times the height of the mercury. And that should equal, because they're the same pressure, the density of iododecane times gravitational acceleration times the height of iododecane. G would be the same in both cases. So if we want to know the height with respect to iododecane, then what we have to do is just solve for H of I, which then would be density of mercury times the height mercury divided by the density of the iododecane. And then we can plug in numbers here. Density of mercury is not given here, but you can look it up. It's 13.6 grams per cubic centimeter or per milliliter, and then times 749 millimeters. And then the density of iododecane was 1.2 grams per milliliter or cubic centimeter. So these units cancel, and you can see now that the height is going to be 88.7 millimeters. We can convert this to meter and just get our final answer to be 8.49 meters. So you can see that with this liquid, which is a lot less dense than mercury, the height of that barometer would be much more compared to when you're using mercury. So for that same pressure, if you think about this being the mercury barometer, the height would be, say, this much. We use the iododecane liquid as the measure of the pressure, then that same pressure would give you a height of that much. Okay, so this would be 8.49 meter. That one would be 749 millimeter or 0.749 meter. Okay, so that sort of tells you the difference between those two liquids. Now the question is then, when would it be appropriate to use that second liquid, the iododecane? Well, sometimes you're going to need this if you're measuring small differences in pressure, right? Because the mercury, it takes quite a bit of pressure in order to move it up, 1 millimeter. But this one, you can clearly see it better because there's a lot more height that you can use to measure small changes in pressure. So when would be appropriate time to use the iododecane barometer? When small pressure changes are being measured. Okay, so that's the answer to that second question.